Okay, good day everyone. So we are here today to discuss on the stiffness method, thrust analysis. We will analyze thrust analysis using stiffness matrix method. This is actually week number 6 or 7. Week number 7, right? Okay, so we will continue thrust analysis. So I believe you have watched my videos regarding this topic on how to establish the element stiffness global matrices and the structure stiffness matrix. So we will continue to analyze unknown displacement and unknown reaction, as well as member forces in thrust. Okay, so stiffness method is actually another method to analyze indeterminate structure. So if we have flexibility method to analyze indeterminate structure, we also have another method called stiffness method. And stiffness method is actually one of the popular method in the world, because this is actually the theory behind all structural engineering software. Okay, there are quite many advantages compared to flexibility method, because stiffness method beside this is the easiest, because it is based on the matrix calculation, multiplication. In this method, you don't have to apply moment, taking moment at A, at B, and so on. We don't have to do that. What we are going to do is we will use the appendix given. You will be given appendix in final exam. And the formula also is given in the textbook. You can also refer to the formula. So basically, stiffness method, we will apply some procedure. We will apply some procedure in order to establish stiffness matrix. And from the stiffness matrix, we will continue to calculate unknown displacement and reaction at the support. Okay, compared to flexibility method, if in flexibility method, the outcome or the goal is to calculate forces, but in stiffness method, the first aim is to calculate displacement. Displacement is the objective. Displacement is the goal. So we will determine unknown displacement. We will determine unknown displacement using stiffness method, and after that, we will substitute the unknown displacement into force displacement equation. Then we will continue to calculate unknown reaction. Okay, please watch back my recording. I have few video explaining about the lesson, the learning outcome, how to establish the element global stiffness matrices, as well as how to establish the structure stiffness matrix. Okay, so for this session, we focus on how to calculate unknown displacement as the first objective. The second one is to calculate reaction in thrust, and after that we will calculate the member forces in thrust. Okay, all will be using matrix multiplication. So we will start with reviewing some of important things that you can get from the textbook. Okay, here please refer to chapter number 14 in the Hibler textbook. Okay, about the fundamental. So you have to understand about the member and node identification. What is the global coordinates? Because we will deal with global coordinate system. Because as I said previously, just now I said that this is the method used in all structural engineering software. And as far as you know, when we need to model any structure using software, we will have to have the coordinate. We have to understand the coordinate system. Okay, so it will be based on the global coordinate system. We have two coordinate system, member or local coordinate system. We also have global coordinate system. And the procedure will be using the global coordinate system in order to get K. K is stiffness matrix, K for the structure. Okay, so this is some explanation about member stiffness matrix. Okay, of course you don't need to understand how they derive the equation. Okay. Okay. So the explanation shown here is how this formula is derived. This is actually what we call as member stiffness matrix. This is member stiffness matrix. Member stiffness matrix. Okay, we have 4 by 4. It is 4 by 4 matrix. 4 by 4 matrix. 2 belong to near end and another 2 belong to far end. Because in one element we will have near end, we will have far end, and each node has 2 degrees of freedom in X and in Y for truss. So that is why for the member stiffness matrix we have 4 by 4. It must be 4 by 4 for truss, as well as beam and frame will have 6 by 6 matrix. Okay, so this is the formula that you are going to use when you analyze truss. So this lambda can also be written as C. Okay, because if you look to another textbook, or if you look at to past exam papers, okay, you may find that we use the symbol C. Okay, C. So C and lambda is actually equal. Okay, so I don't mind if you want to use C because C is easy to write, right? Okay, so this is 4 by 4 matrix. 4 by 4 matrix, please look at the formula. This 4 value is actually equivalent to this 4 value. Okay, and this 4 also will equivalent to this 4 value. And matrix means we have to apply all the metric characteristic, means that this is the, okay, the matrix is symmetry. Okay, line number 1 equal to row number 1, like what we have done in matrix topic in mathematics. Okay, so this is the formula. So K, the member stiffness matrix K, will be depending on AE, which is called as axial rigidity. L means length for each member. So we calculate element stiffness matrices, and we combine to have the structure stiffness matrix. Element stiffness matrix we label as small letter. Element stiffness matrix we use small letter K1, K2. And to determine structure stiffness matrix, so we use capital K. So capital K is for structure stiffness matrix, and it is combination of member stiffness matrices. Okay. Okay, let's look at the example. Okay, example 14.1. I have more than one video explaining about this. Okay, so I want you to watch that one. Okay, so when we want to analyze K will be depend on EA, will be depend on L. Okay, so that is why inside this example there is no loading, because K is depending on axial rigidity as well as length of the member. Okay, so what we need to do is we have to establish, since there are 1 and 2 element, element 1, element 2. So we will produce K1 and K2, K1 and K2. This is K2. Okay, so this value we get from formula given just now, from the formula. Okay, from the formula, this value. And what most important is the degree of freedom label. Degree of freedom label, this one. Degree of freedom label. This label is very, very important, because if you don't write this label correctly, you will get wrong structure stiffness matrix. Okay, so this will be labeled based on near to far end condition. Near to far end condition. We will have near X, near Y, far X, far Y. So we will label according to this. Okay, 1, 2, 5, 6, 1, 1, 2, 5, 6, this is for K2, and 1, 2, 3, 4, this is for K1. So we get this from the free body diagram. We get this from the free body diagram. Okay, this is the free body diagram. And in the free body diagram, we should have 5 important things. Number 1, we have to make sure that in the diagram it has node number. And node number is actually join number, join name ABC. In stiffness matrix, we use label in numbering 1, 2, 3. Okay, number 2, we should have element number. Element is member, and member also we have to label in numbering, element number. Okay, conventionally we refer it as member AB, member CD, but in stiffness matrix method we will call it as element number. So we have element number 1, element number 2. Okay, number 3, we have to label what we call as degree of freedom. Degree of freedom in thrust, there are 2 degree of freedom in X and Y direction, and this direction is compulsory. This direction is compulsory, X and Y. So this this is called as 2 degree of freedom per nodes. 2 degree of freedom per node. So that is why we have, since we have 3 nodes, we have 2 here, we have another 2 here, we have another 2 here. So that is why the total degree of freedom in this thrust is 6. So this 6 will be labeled according to constrained and unconstrained degree of freedom system. Constrained and unconstrained degree of freedom system. Constrained and unconstrained degree of freedom system. So watch the video to understand about constrained and unconstrained degree of freedom system. Basically, constraint means support. So there are 2 pin here, 2 pin representing 4 unknown reaction. 2 pin representing 4 unknown reaction. 4 unknown reaction refers to 4 DOF in constraint system. So we have 2 DOF in unconstrained system. 2 DOF in unconstrained system. So by looking at this diagram, 2 is unconstrained. So we label as 1 and 2. We have to label unconstrained first. Followed by constraint. Because the first objective is to determine displacement, and displacement occur in unconstrained system. That is why we need to label 1 and 2 first, then only followed by DOF in constrained system. So this is how we determine the structure stiffness matrix. So we have 6 here. This is 6 by 6 matrix, and this 6 by 6 matrix will be written in order. This 6 by 6 will be written in order 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Even though for the member stiffness matrices, we have to label based on near and far end condition, but to determine the structure stiffness matrix, we have to combine and we have to write it in order. Okay, so this is the structure stiffness matrix, and this is very, very important, because if you get wrong structure stiffness matrix, you will get wrong displacement, wrong reaction, wrong member forces. Okay, this is very important. Okay, we move to another example given here, 14.2. 14.2, determine the structure stiffness matrix. The structure stiffness matrix means capital K. The structure stiffness matrix means capital K. So K is actually come from combination of element stiffness matrices K1 plus K2 plus K3 plus K4 plus K5. Okay, we have to plus all element. Each element has their own matrices. Okay, 5. So here we have K1, K1. So K1 label as 1265. Okay, this label will depend on the support condition, constrained and unconstrained. Okay, and we have K2, K2 label as 1278. Okay, then K3, K3 label as 1234. And K4 label as 3478. And K5. K5 is labeled as 34565. 3465. Okay, and there are 6 elements. Okay, doesn't matter, there are 6 elements. So 6 is 6578. So this is the degree of freedom level. Degree of freedom level. And based on this diagram, there are 6 elements. There are 6 elements. That's why we have K1 until K6. And from this 6 element stiffness matrices, we have to produce the structure stiffness matrix. The size of the matrix will be, there are 1, 2, it is 1, 2, 3, 4. 4 means 4 times 2 because truss has 2 per node. 2 degree of freedom per node in X and Y component. So we will have 8 by 8 matrix. We will have 8 by 8 matrix. So we get combination of K1 until K6. So we will get 8 by 8 matrix. And for the structure stiffness matrix, this one, it always written in order. And 1 until 8 in order. But not for element stiffness matrices. Because for the element stiffness matrix, we will label from near to far. From near to far. Okay, so this is just about how we establish element stiffness matrices. And of course, the objective to use stiffness method is to analyze. Analyze means we will determine displacement, we will determine reaction, we will determine internal forces. And one of the advantages of using stiffness method is we can get these three output, displacement, reaction, and internal forces using one method called stiffness method, which flexibility method cannot. In flexibility method we cannot get displacement. We only can get reaction at the support. But by using stiffness matrix method, this is the method. When we use the method, we can get all the output, displacement, reaction, and member forces using only one method, using what we call as stiffness equation or force displacement equation. So this is the force displacement equation. Q is force, K is the structure stiffness matrix, K is the stiffness coefficient, okay, D is displacement. Q is force, D is displacement. Q force, D is displacement. Q force, D is displacement. This is force. This is displacement. So this is called as force displacement equation. Force displacement equation, and D and K is the stiffness coefficient. Stiffness coefficient. Sama macam flexibility method, we have flexibility coefficient, stiffness coefficient. Okay. So we have force displacement equation. We have force displacement equation, and force displacement equation is the stiffness equation. Flexibility method, we have compatibility equation. Compatibility equation is flexibility equation. But in stiffness method, we have force displacement equation, and force displacement equation is stiffness equation. Okay? And actually, this is the formula to calculate member forces. Member forces. Reaction we get directly from force displacement equation, but for member forces, we have to remember this formula. Okay, this one you have to remember. Okay, this is the formula to calculate member forces in the truss. Okay, so this is the procedure. Please read on your own. Okay, so basically I have copied this and put into stiffness method. Okay, and another advantages beside just now I said that stiffness method can be we can get all the output using one method called stiffness method. We can get all displacement, reaction, and internal forces in truss using stiffness method. Okay, another advantages of using stiffness method to analyze structure is we can use stiffness method to analyze both determinate and indeterminate. If flexibility method we apply whenever equilibrium equation is not enough to calculate unknown reaction, but in stiffness method we can use it to analyze both determinate and indeterminate. So we will start with this one first. So this is the truss. The truss has two elements. It has two pin support. Okay, pin support. Support relates with constraint condition, constraint degree of freedom. Okay, joint is called as node. Member is called as element. Okay, and we have to number one, label the nodes. So we have to label. Okay, node. There are 3 nodes here, as we can see. 1 here, 2, and 3. Label. Okay, you can label the other way around. Doesn't matter. The most important thing is it has label. 1, 2, and 3. Okay, 1, 2, and 3. Label. Okay, there are 3 nodes. Means that if this is 3 nodes, so it will produce 6 degree of freedom. 6 degree of freedom because there are 2 in each node. Okay, so we have 2 element. Element consists of 2 nodes, near and far. This is element. Element consists of 2 nodes. One element consists of 2 nodes. Okay, so when we combine 1 and 2, it become 1 element. When we combine 2 and 3, it become another element, 1 element. So we have element 1 here, element 2 here. So this is how we write. Okay, how we write the element name, the node number, because we have to differentiate. All will be using number. Because this is the theory behind structural engineering software, and when we use software, normally we will deal with so many nodes number, so many elements. So that is why A to Z is not enough. So that is why all we will use numbering. Okay, so there are 3 nodes. There are 2 elements, 1 and 2. We written in the box referring to the element. Okay, not in the circle referring to the nodes. Okay, so 3 by 2, it is equal to 6 degree of freedom. 6 degree of freedom. And we have to label the 6 degree of freedom according to unconstrained constraint. So in order to label, we have to make sure that we label it correctly. Label correctly means we have to label unconstrained first. Unconstrained degree of freedom first. Then only we label constraint. Degree of freedom. Total must be 6. So normally what I will do is like this. So I will sketch two diagrams separately. Okay, separately like this. Okay, so represent the same truss, but we do it separately because we will label one start from unconstrained. Okay, so by looking at the diagram, so we know that there are four unknown reaction, and four unknown reaction means 4 DOF in constraint system. Four unknown reaction. Four unknown reaction means unknown reaction we identify from support. There are two pin support. So we know that there are four unknown reaction. So four unknown reaction means 4 DOF in constraint system. So now if in constraint system there are 4, so the remaining is 2. So 2, there are 2 DOF here. Okay, total will be 6. So we have to label 4 in constraint at support. Here is 2 and 2. Representing node number 1 and node number 3. There are 2 pin support, one at node number 1, one at node number 3. So we have to draw or sketch the degree of freedom in constraint system representing support. Okay, and we have to complete another 2 in unconstrained system. Like this, always. We have to always do like this every time we want to analyze either frame, either truss, either beam. Okay, we have to sketch it separately so that we do not make mistake. Okay, because we need to label start from unconstrained. So it will be 1 and 2. Label start with 1 and 2 in unconstrained system, then only followed by 3, 4, 5, 6. Okay, you can also put like this, 3, 4, 5, 6. Doesn't matter. Okay, like this. Okay, so now we know that at node number 2 it has 1 and 2, and then 3, 4, and then 5, 6. Okay. Next thing that we need to put into the diagram is the arrow. We have to put arrow which is parallel with the member. Okay, we have arrow for element number 1, we have arrow for element number 2. So this arrow is very important because we identify near and far end condition based on the arrow. So the arrow ni we can put in any direction that we like, doesn't matter. So arrow is always going towards far end. So having this, of course, this one will be far because the arrow is always going towards far end, and here is near end. Okay, so by putting the arrow, it will guide us to identify for each element which node will be near, which node will be far. And this is very important when we want to calculate lambda x, lambda y, or cx and cy. Okay, and also for the labeling, because we label start from near to far. Okay, so the arrow. And another thing that is important before we start calculate the element stiffness matrices is the coordinate. So we have to choose one node as origin, that will be 0, 0, and we will label the remaining. Okay, so we choose 2 as origin. So this will be 0, 0, 0, 0. So based on the origin, we can label node number 3 as 3, 0. And we can label node number 1 as 3, 4. Okay? So these are the things that must be putting into the diagram before we can start use the formula to calculate Cx, Cy, and after that we will establish the structure stiffness matrix. Do like this all the time you want to analyze stress using stiffness method. Okay, so we will start with calculating Cx and Cy for each element. Cx and Cy for each element. Okay, so I want to make it short because you can watch the previous video where I have discussed about Cx and Cy. But this time I want to summarize Cx and Cy in table form. So we have two element. We have two element. So each element has its own length. And we have Cx and Cy or lambda x, lambda y. I prefer to write Cs, Cx, Cy. So this is Cx and Cy. So this is Cx and Cy. Cy. Two element. Okay. So Cx and Cy. Okay, we have element 1. Element 1 joining node number 2 and node number 1. Okay, length of this is 5 meter because we have 3 and 4, so it is 5 meter length. 5 meter length. Cx, Cy. So Cx and Cy, beside having formula sin theta x, cos theta x in appendix, so actually we can easily determine Cx and Cy by referring to the coordinate. So if we want to calculate Cx, please look at the x coordinate. When we want to calculate Cy, please look at the y coordinate. Okay, so it is far n minus near n, far x minus near x, far x minus near x. So far, okay, looking at element number 1, this is element number 1. Looking at element number 1, far is 3, near is 0. Far is 3, near is 0. Far is 3, near is 0. We get 3 as far because we refer to the arrow. So it is 3 minus 0. We have to divide by L. It is 3 minus 0. 3. It is 3 minus 0. It is 3 minus 0. 3 minus 0 divided by length is 5. So we get this as 0.6. 0.6. Okay, what about Cy? So for Cy, we have to look at the y coordinate. It is 4 minus 0. It is 4 minus 0. It is 4 minus 0. divided by 5. If you put the arrow the other way around, so you will get negative value. Doesn't matter. Both can be accepted. Okay, so this will be equal to 0.8. This will be equal to 0.8. Okay, and for element number 2, length is 3 meter. Length is 3 meter. Okay, CX and CY. So look at element number 2. Element number 2, 3, it is 3 minus 0. Look at X coordinate, 3 minus 0. Look at the arrow. Okay, the arrow is always going to the far end. So 3 will be far. So it is 3 minus 0. 3 minus 0. Divide by 3. So this is equal to 1. And for CY value, look at Y coordinate. Look at Y coordinate. So it is 0 minus 0. It is 0 minus 0. Divide by 3. And this is equal to 0. So this is how we determine C and CY. So please don't try to remember the formula. Okay, just follow the step like this. Okay, to identify CX, look at X coordinate. To identify CY, look at Y coordinate. So it is far minus near. Far minus near, we divide by L. Okay, we divide by L. Okay, so we will establish K1. K1 means this. K1 means this. This is not number 2, not number 1. This is element number 1. In element number 1, 2 label as 1 and 2. 1 label as 3 and 4. The arrow is like this. Okay. So we will establish now the stiffness matrix. The stiffness matrix. Okay. The stiffness matrix, for the stiffness matrix, for element stiffness matrix, we will label using the small letter element. K for element will be labeled as using small letter. K for structure stiffness matrix will be labeled using capital letter. So this is for element. So we use small letter. So it is K1. Here it is K1. Remember small letter because it is for element K1. Formula, for the formula, okay, wait. Okay. So we use the formula. We will use the formula shown previously in the textbook. Okay, in the textbook, this is the formula. Okay, lambda or C is equal. Lambda or C is equal. So it is okay. So the formula is actually like this. The formula it is C or lambda C X C X. Formula ni you don't have to remember. So it is given. It is given in appendix. CX square CX CY. C X CY. CX CY. Okay, since it is symmetry matrix, so the formula is like this. Sorry. CX, here is CXCY. Here is CXCY. Okay, so this. Okay, please refer to the formula. So CXCY. And we have CY square. CY square. So this is CY. Or lambda Y. CY square. This one is negative. This one is negative. Okay, so this is actually the formula. Okay, this is the formula. Okay, this is the formula to calculate K1, it is AE over L. AE over L, so AE over L, AE over L. Okay, so this is the formula. So we just need to substitute CX and CY for element number 1 into this, and we will get the element stiffness matrix for element number 1. Okay, so we solve this. Okay, remain AE constant. It is AE over L is 5, so we replace L with 5. Okay, CX square, Cx square means 0.36. Cx square means 0.36. 0.36. 0.36. This is negative 0.36. Negative, this is positive 0.36 and negative 0.36. Cx, Cy. Cx, Cy. Cy square, Cy square 0.64. 0.64. Cy square is 0.64. Okay, 0.64. 0.64. This one is negative 0.64. Negative 0.64. And this one also negative 0.64. Okay, and Cx times Cy is 0.6 times 0.8. 0.6 times 0.8 it is 0.48, right? 0.48. 0.48, so 0.48 here. Where is another? So this is also 0.8. This is also 0.8. This is also 0.48. Okay, this is negative 0.48. Negative 0.48. Negative 0.48. Negative 0.48. Okay, so this is actually the stiffness matrix. The stiffness matrix for element number 1. Element number 1. So you will get this. We get this. And we simplify this. We have to divide by 5. We have to divide by 5. It is 0.36 divided by 5. So what do we get when we divide 0.36 by 5? Okay, now we remove 5 here. We have to remain K in terms of AE. So we have to divide all the value by 5. It is 0.36 divided by 5. What do we get? Zero point 0.36 divided by 5.
0.072.
0.072. Okay, it is 0.072. 0.072 here, also 0.072. This one is negative 0.072. So it's here. 0.072. Okay, 0.48 divided by 5. 0.096. 0.096. 0.096. 0.096. This one is negative 0.096. This is also negative 0.096. 0.096. Okay. So this one also 0.096. Negative 0.096. It is symmetry, yeah. it is symmetry 0.096, and this one also. Okay, what about 0.64 divided by 5?
0.128.
128. 128. This one is negative. This one is negative. Okay. Okay, now, so this is the element stiffness matrix for element number 1 or member number 1 in terms of AE. Okay, this is the matrix. However, what most important is we have to label the degree of freedom according to near and far end condition. Okay, we have to label based on this label. Okay, we have to label degree of freedom. We have to label degree of freedom start from near and near to far. Near xy, far xy. Because at near node we have x and y. At far node we have x and y. So we have to label based on this order. Near xy, far xy. Near xy, far xy. So we will label as near is 1 and 2 is the label for xy at near node, and far 3 and 4. So it is 1, 2, 3, 4. 1, 2, 3, 4. Okay, there are lots of video explaining about this. Please watch, because we don't have enough time to cover all, because we have so many cancel class. Okay, please watch the video in order to learn how to label or how to establish element stiffness matrices. Okay, we will label this as 1, 2, 3, 4. Near xy, far xy. It is 1, 2, 3, and 4. 1, 2, 3, 4. One, two, three, four. We have to label both, not only the vertical one, the horizontal also. Means that yang ni pun kena label 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Near xy, far xy. Okay, now we move to K2. We move to K2. So this one is 1, 2, 3, 4. So now we move to K2. Okay, K2, L is 3 meter. L is 3 meter. L is 3 meter. Okay, we have AE, L is 3 meter, L is 3 meter, CX is 1, CY is 0. So we get like this. Okay. Okay, I make it shorten. So this is AE. So please use the same method like we have done for K1 to determine K2. Okay, so it is 0.333, 0, negative 0.333, 0, okay, we have 0, because CY is 0, so anything related to CY will be 0, 0, 0. And then this one is 0.333, 0, 0. Okay, remember it is symmetry matrix. It is symmetry matrix. So this one should be 0 as well. This one also 0. Okay. So use the formula to calculate this, but again, the most important part is the degree of freedom label. The degree of freedom label, so we refer back to the diagram. So look at element number 2. Look at element number 2. Element number 2 consists of node number 2 and node number 3. The arrow is going towards far end. Far is 3. Far is 3, near is 2. So we will label degree of freedom as 1, 2, 5, 6. 1, 2, 5, 6. 1, 2, 5, 6. So here we label as 1, 2, 5, 6. 5, 6. 1, 2, 5, 6. So same, we need to label the horizontal one as well. 1, 2, 5, 6. So this is K2, K1 and K2.
Doctor mute.
Okay, so since we have K1 and K2, this is the element stiffness matrices for element number 1 and for element number 2. Remember, when we analyze structure using stiffness method, what we should do is we actually divide the structure into element. We divide the structure into element. That's why we do this. Okay, original is structure truss. We divide into element. We produce element stiffness matrix K1 and K2. Then when we want to analyze the whole structure, we want to analyze displacement, we want to analyze reaction at the support, we have to combine back these element stiffness matrices to produce structure stiffness matrix. We have to produce structure stiffness matrix. So we have to combine. So we will produce 6 by 6 because there are 3 times 2, 6 matrix. 6 matrix we combine. Remember all this value inside K1 and K2. Labeling is important, and this is actually the position of the value. We will have 1 to 1. We will have 6 by 6, means that we have the value for 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 until 6, 6. It is matrix. It is symmetry. So we have to combine this K1 and K2 to produce 6 by 6 matrix. We produce 6 by 6 matrix. So we will use capital K to represent the structure stiffness matrix. Okay, so now we will have stiffness matrix. Means that we will combine K1 and K2. We will combine K1 and K2. Okay, K is capital K. K is capital K. Capital is for structure. Small letter is for element. Okay, K in terms of AE, so it has 6 by 6. It has 6 by 6. It has 6 by 6. So the label, the degree of freedom should be 1 to 6. The label should be 1 to 6. Okay, it is 6, 6. This is for the label lah. So it is 1 to 6. 1 to 6. Okay, 1, 2, 3, 4, 5, 6. 6. Okay, this is for label. This is for label. Remember, label ni we label horizontally and vertically. 1 to 6. Okay, so find the value for 1, 1 from K1 and K2. From K1 and K2, find the value for 1, 1 in the structure stiffness matrix. What is the value? Do you get what I mean? We want to find the value 1, 1 until 6, 6. We find the value from K1 until K2. So please find the value at position 1, 1 from K1 plus 1, 1 at K2. Find the value and total. It is just simple mathematical calculation. 1, 1 means this one plus this one, 1, 1. So please find each value from 1, 1 until 6, 6. From 1, 1 until 6, 6. 1, 1 until 6, 6. In this matrix, we find from K1 and K2. You have to do it one by one. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, until 2, 6, until you 6, 6. Please find the value and put into the structure stiffness matrix. Okay, so what is the value at position 1, 1? It is 0.002 plus 0.333. What is the value?
Zero point
0.405.
Okay, 1, 2. 1, 2.
0.072.
1, 2. 1, 2. 1, 2 to 1 is the same. 1, 2. Can you see? 1, 2 is 0.096. 2, 1 also 0.096. 2, 1 also 0.096. So what is the value? What is the value? One, two. It is 0.096. 1, 3. 1, 3. What is the value for position 1, 3? Lama ke nak tengok value kat sini? Is it taking so long? This is the value for 1, 3. This is the value for 1, 3, 1, 3. We don't find 1, 3 in K2. We only have 1, 3 in K1. So that is the answer. Don't take it so long because you have another long journey to do. This is just the first part of analysis. So what is the value for 1, 3? Again, what is the value for 1, 3?
Negative 0.072.
Negative 0.072. 1, 4. 1, 4.
Negative 0.096.
Yes, negative 0.096. 1, 5. 1, 5. and 1/6. Okay, then 2, 2. 2, 2. 2, 3. 2, 3. Then 2, 4. 2, 4. 2, 5. 2, 5. 2, 6. Sorry. 2, 5. 2, 6. It is 0, 0. Okay. Continue with 3, 3. Continue with 3, 3. So 3, 3 is 0.072. 0.072. 3, 3. 3, 4. Then is 3, 4. 3, 4 is 0.096. 0.096. 3, 5. 3, 5. 3, 5. Can you find 3, 5 in K1? Can you find 3, 5 in K2?
No.
No. Means no intersection. It is 0, 0. We move to 4, 4. 4, 4. So it is 0.128. 0.128. 4, 5. 4, 5. 4, 6. 4, 5. 4, 6. No value. And then 5, 5. 5, 5 is 0.333. 4, this is 5, 5. 5, 6. 5, 6. What is the value for 5, 6? What is the value for 5, 6?
0.
0. That is why labeling, degree of freedom label is very important. Okay, this one is 0. 6, 6 is also 0. Okay, this is metric. Metric is symmetry, so we can write the stiffness matrix like this. Okay, we can write like this. Diagonal Okay, symmetry tu dia in this direction. Not this direction, not this direction. It is diagonal. Okay, like this. Okay, so this is the structure stiffness matrix. The structure stiffness matrix for the truss. Okay, you cannot get this if you don't label the element stiffness matrices according to the degree of freedom correctly. So make sure you label it correctly. That is why this step is very important, because it will be depend on how we label the degree of freedom according to constraint and unconstrained system. Okay, so next after this is we will apply what we call as force displacement equation. We will apply what we call as force displacement equation or stiffness equation. It is force displacement equation or we also call this as stiffness equation. Okay, force displacement equation is Q is equal to KD. Q is equal to KD. Q is equal to KD. This is the basic one. Q is equal to KD. Q is equal to KD. Means that beside doing this, calculate stiffness matrix, we have here Q and D. Q is force, we call it as nodal forces. D is displacement, we call it as nodal displacement. Nodal forces and nodal displacement means that we will have six value of Q and 6 value of D, because dia akan sama dengan number of K, 6 by 6, number of degree of freedom. 6 by 6 matrix means that we will have Q from Q1 until Q6, and we will have D from D1 until D6. All this will be written in matrix form. Q will be written in matrix form. D will be written in matrix form. Q will have Q1 until Q6. D will have D1 until D6. Okay, 1 to 6 is degree of freedom, the position at nodes. So we have Q1 until Q6. Q is nodal forces. D is nodal displacement. Nodal forces and nodal displacement. Nodal forces and nodal displacement. We have Q, we call it as nodal forces. And we have D, we call it as nodal displacement. Nodal displacement. Nodal displacement. Nodal forces and nodal displacement. Okay, means that we will produce Q1 until Q6, D1 until D6. So here we have what we call as nodal forces. It is Q, capital Q, because it is for the structure, for the whole. Q equal to 6 value of Q. 6 value of Q. Position dia sama position ni, 1 to 6. 1 to 6. Okay, so inside this there are 4. Inside nodal forces there are 4 unknown reaction. Inside nodal forces there are 4 unknown reaction. Inside nodal forces there are 4 unknown reaction. 4 unknown reaction in constraint system. Degree of freedom in constraint system representing number of unknown reaction. Degree of freedom in constraint system representing number of unknown reaction. There are 4 unknown reaction. We will label as Q apa? For constraint system. Use the label that you can see right now. Q apa ni? Label apa yang you nampak kat sini? What is the numbering that you can see in this diagram right now?
4 and 3.
3, 4, 3, 4, 3, 4,
6, 5, 5, 6.
5, 6. 3, 4, 5, 6. So 3, 4, 5, 6 means the location of unknown reaction. So there are four unknown reaction. There are four unknown reaction at position 3, position 4, position 5, position 6. So it is Q3, Q4, Q5, and Q6. So here is Q reaction at the support we use capital Q 3, 4, 5, 6. Because this is the unknown. We do not know the value yet. We do not know the value yet, and we know that reaction is the output. We will calculate unknown reaction later on. So since we do not know the value yet, so we just write like this, the symbol Q at position 3, 4, 5, 6. Nodal forces. And this 3, 4, 5, 6, this 3, 4, 5, 6 is actually the position that is located in the constraint system. Okay, so we have Q1 and Q2. Means that setiap satu Q ni, Q1 sampai Q6, you have to be able to see it. Okay, to see the meaning. To see the meaning. So for example, we have diagram like this. Okay, we label as 1, 2, 3, 4, and 5, 6. This 1, 2, 3, 4, 5, 6 can represent forces. So we have Q1, we have Q2, we have Q3, we have Q4, we have Q5, we have Q6. And in the question, there is a 2 kilonewton downward at node number 2. So this is the force, 2 kilonewton. So we have to be able to read the physical meaning of Q from position 1 to position 6. Okay, so what is the meaning of Q1 until Q6? So siapa boleh baca kat saya? Based on your understanding, what is Q1? Q is forces. Q is forces. So what is Q1 actually? What is Q1? Q1 ni apa? Q1 tu horizontal or vertical? Q1 horizontal or vertical? 1 is referring to horizontal ke vertical?
Horizontal.
Horizontal. Q1 is a horizontal. Horizontal what? We are talking about forces right now, right? It is a horizontal. It is a horizontal force. A horizontal force. This is node number 1, node number 2, node number 3. Okay, now Q1. Look at position 1. And now we are talking about forces. So what is Q1? Q1 is a horizontal force. A horizontal force at node horizontal force at node. Kat mana 1 tu?
2.
2 at node 2. And what is the value? What is
0.
value? 0. Okay. because it is unconstrained. Unconstrained. Okay. Next, what is Q2 meaning? Is a position number 2, horizontal or vertical?
Vertical.
Vertical.
It is vertical. Note 1, 2, 3. Note which note?
2.
Yes, note 2. It is a vertical force at node number 2. It is, can you see the vertical force at node number 2? What is the value?
2.
2 or negative 2?
Negative 2.
Negative 2. Okay, when it is opposite, it is negative. When it is opposite, it is negative. Okay, so what is Q3, Q4, Q5, Q6? What is Q3? Remember 3, Q3, 3 and 4, 3 and 4, node number 1 is spin. Node number 3 is spin. So, when we talking about Q3, it is representing a horizontal or vertical? 3, horizontal or vertical?
Horizontal.
Horizontal what?
Force.
To be specific, because of pin support, horizontal reaction. Horizontal reaction at node
1.
Node 1. And this is unknown reaction. This is unknown reaction. Okay? So you have to understand this. Means that you have to be able to read Q1 until Q6 from the main diagram. Kena baca nilai tu. Q1, Q2, Q3 until Q6. Okay, same goes to D. Same goes to D. And D and Q ni is opposite condition. Opposite condition. Because by looking at the diagram, okay, when we have pin at 1 and at 3, node number 1 and node number 3, logically, due to support, there is no displacement. Displacement is equal to 0. Right? Because of the support. We put support because we don't want we don't want this to move. So displacement is equal to 0. D for displacement. And what happened to displacement at node 2, D1 and D2? Can move or cannot move? D1 and D2. Can or cannot move? At node number 2, there is no support. What happened?
Can move.
Can move. Can move. Okay, so that displacement that we say that it can move, representing unknown displacement. Unknown displacement is the first output. Unknown displacement. So beside having Q1 until Q6, we will also need to identify D1 until D6. So this one is 0 and negative 2. So basically, this is the boundary. So this one is unconstrained, this one is constrained. For nodal forces, constrained belong to unknown reaction, so we leave it as symbol. For unconstrained, we have to replace with number. We have to replace with value. If the value is not given, so we put as 0. But of course, in order to put the value at position 1 and position 2 for nodal forces, we should understand the definition. We should understand the physical meaning like this. Physical meaning. Okay, the physical meaning. Then only we can see what is the value. Okay, so this is for Q. We also have D, and D also must be written in matrix form. Must be written in matrix form. Okay, this is another one is nodal displacement. Nodal displacement. Nodal displacement is capital D. It is actually D1, D2, D3, D4, D5, D6. Okay, so for unknown displacement, it is D1 and D2. This is D1 and D2. Presenting unknown displacement that is located at node number 2. Sorry, D. Okay, D1 and D2. Okay, D1, D2. So what happened to displacement at position 3, 4, 5, 6? Displacement at position 3, position 4, position 5, position 6. What is the displacement value? Apa value ni?
0.
It is 0 because it is support. Okay, same. The definition also same. D1 will be a horizontal displacement. Okay, yang ni Q tadi kan, for Q. For D also same. Okay, sampai 6 lah tu. Okay, so D1 is this is D1 is horizontal displacement. Displacement at node number 2. D2 is a vertical displacement at node number 2. And D3, D4, D5, D6 equals 0 because it is located at support. Okay, so we have this. Then we have, when we have Q, we have D, we have K, so we combine to have one stiffness equation written in matrix form in full. Q is equal to KD, so we will have this. Okay, so this is Q, this is Q equal to K. This is K. D times with D. Okay, time with D. So this is the stiffness equation, force displacement equation. Force displacement equation. Okay, Q is equal to KD. Kalau ada 8, it will be 8 by 8 matrix lah. Okay, now it is 6 by 6 matrix of K. So Q, we have Q1 until Q6, D also D1 until D6. The first output is the unknown displacement. The second output will be the unknown reaction. The third output will be member forces. Okay, so we can solve this D1 and D2. We can solve this D1 and D2 by solving simultaneous equation. There are two unknowns, so we have two simultaneous. We will use two simultaneous equation. Okay, actually, we have to multiply all. But since D3 until D6 0, so it is just like we cancel all 0 lines, 0 rows. Okay, so this is 0, 0, 0, 0. So we don't have to consider this because when we consider, we get 0. So cancel all 3, 4, 5, 6. Cancel all 3, 4, 5, 6. So what do we get is only equivalent to two simultaneous equation that we can solve using calculator. 2 by 2 only. Okay, so what we get is just like this. Okay, so this one is called as stiffness equation. This is stiffness equation. Or force displacement equation. And to solve for the unknown displacement, okay, we consider only because of the zero displacement, because of the zero displacement at support, we consider only unconstrained system. Constrained degree of freedom system. And it is only true when all displacement at support equal to 0. Okay, so what we get is 2 by 2 matrix only. So it is 2 by 2, 8E times, okay, and this is D1 and D2. Okay, this one is 0 and negative 2. So this is D1 and D2. And then we have 0.405, 0.096, 0.096, and 0.128. Okay, so solve this. We get D1 and D2. If we don't have AE, doesn't matter. We will get D1 and D2 in terms of AE, per AE. So we get D1 and D2, which is equal to, okay, please key in into calculator. A1 is 0.405, yeah. A1 is 0.405, A1 B1 is 0.096, C1 is 0, A2 is 0.096, B2 is 0.128, and 2. It is two simultaneous equation. It is equivalent to two simultaneous equation. So we get the answer per AE. Okay, what is the value for D1? For D1 and D2. What is the answer? Please calculate. What is the answer for this? In terms of AE, what is D1, D2? Apa nilai ni?
One negatif 0.05.
0.05? D2?
0.28. 0.24.
Is it right one? Yang lain? So we get this Macam mana calculate tadi? Check balik Okay. Because we don't have AE right now. So we just need to solve and give the answer in terms of AE. Check balik Okay. Kalau dalam buku, you can check of course in the textbook, tapi yang dalam textbook tu loading the value the unit is different, doesn't matter, but still have the same numbering. We just change the unit 3 and 4 feet to K. So we just change to 3 meter, 4 meter and to K. So it is 4.505 and negative 19.003 divided by AE. So this is the unknown displacement. If we don't have AE value given. Okay. So this is the answer for D1 and D2. And after that, we have to continue to calculate. Okay, we will use this equation to calculate Q3 until Q6. Use matrix multiplication to calculate Q3 until Q6. To calculate Q3 until Q6. So what is Q3? Now calculate Q3. Can you calculate Q3? Can you calculate Q3 after you have determined D1 and D2? Can you now calculate Q3? Calculate Q3 using this. Q3 means kita nak kali nilai ni. 3 ni kan. But don't forget 3, 4, 5, 6 dah 0. Okay, 3, 4, 5, 6 dah 0. So yang ni matematik je lah. So yang ni negative 0.072 and negative 0.096. Negative 0.072 and negative 0.096 times with D. It will cancel AE. It will cancel AE. So what do you get for Q3? Q3, it is negative 0.072 times with 4.505 plus with, it is negative 0.096 times with negative 19.003. Okay, AE will be cancelled. So this is the answer for Q3. And we will do the same to calculate remaining Q4 until Q6. Okay, that is how we calculate reaction. It is just mathematical calculation using force displacement equation. Yang ni sebab kita tak tulis full. Actually, we can write in full. Cuma kalau you nak write in full, okay, it will take quite some time, long time to just write all the value. So that is why I suggest you to write like this. Okay, and all this has value. So when we need to use this value, so we just need to find the value from this. Carilah value tu kat atas ni. Okay. So solve using simple mathematical calculation. It is multiplication to find Q3 until Q6. Okay, Q3 until Q6. That is reaction at the support. And after that, we can continue to calculate member forces. And for member forces, we have to use formula and we have to remember the formula. Okay, when we want to calculate Q for element number 1, and since this is member force and member, we always use small letter to represent member. Capital letter we use to present structure. So the formula is AE over L. Okay, it is matrix 1 times 4. Okay, refer to the formula. It is 1 times 4. Okay, trust ni soalan wajib dalam exam ya. Trust confirm masuk exam. Soalan wajib dalam exam. Okay, ni formula. So you have to refer back to the formula given. Okay, refer to the textbook, refer to the appendix as well. Okay. So this is D eh. Yang ni CX CY, yang ni D. Yang ni CX CY. Yang ni D. D ni akan follow balik di K1 punya position. K1. Dekat K1 tadi, K1 we have 1, 2, 3, 4. K1. 1, 2, 3, 4, K1. So we will have to put the D1 until D4 value kat sini. We will follow whatever label that we use in K1. For K1, we have 1, we have 2, we have 3, we have 4. For K1. Okay, so this is D. D. This is formula lah. Okay, and we have CX and CY. CX and CY. No need this one. CX and CY. So this is the formula. The formula is negative CX, negative CY, CY, CX, CY. This is the formula. CY. So this is the formula. So to calculate Q1 means member force for element number 1, we just need to substitute all the value that we have actually calculated. Okay, we have AE, we have L for element number 1 is 5, CX and CY is 0.6 and 0.8. This one is negative 0.6 and this one is negative 0.8. Negative 0.8. So this is 0.6, 0.8. And D1 we get 4.505. 4.505 and negative 19.003. So this one is divided by 1 over AE. 1 over AE. Okay, so we simplify so we get D3, D4 is equal to 0. D3, 0, D4 is equal to 0. So this will be the answer for Q1. Okay, Q1 is AE over 5. So we calculate this, we get it is negative 0.6. 0.6 times with 4.505 negative negative plus, okay, plus with 0.8 0.8 times 19 0.003 okay, we divide by 5. Okay, so we get the value of Q1 equal to 2.5. This is 2.5 kilonewton. So this is member forces. So we will continue to calculate Q2. Okay, so this is basically what you are going to do in stiffness method for truss. So this is the basic one where we do not consider yet the temperature changes effect, temperature changes, fabrication error, as well as support settlement. This is the basic one where we use Q is equal to KD. So first step is you have to draw the free body diagram. Complete this diagram with degree of freedom label, node number, element number, put the arrow as well as coordinate, and then identify or calculate Cx, Cy for each element, and use Cx, Cy to calculate element stiffness matrices K1 and K2, since we have two element, and in element stiffness matrices, the most important part is to label the degree of freedom for element correctly. We label from near to far, near xy, far xy. That's why we get 1, 2, 3, 4 for element number 1 and 1, 2, 5, 6 for element number 2. We combine this K1 and K2 to get the structure stiffness matrix. The structure stiffness matrix will remain in terms of EA or AE, and K for the structure stiffness matrix will be labeled using capital letter. For element, we label using a small letter. Okay, so once we have established the structure stiffness matrix, we have to identify the nodal forces and nodal displacement. So and then we combine to have the force displacement equation like this. So from force displacement equation, so we solve this, and since displacement at position 3, 4, 5 and 6 equal to 0, so it is just like we only consider unconstrained system, and then we solve using simultaneous equation, and since AE is unknown, is not given, so we remain D1 and D2 in terms of AE. And after that, we use back the stiffness equation. We calculate Q3, Q4, Q5, Q6 as 4 unknown reaction in the truss. And we use D1, D2 as well to calculate the member forces using this formula. So basically, this is all about stiffness metric analysis, stiffness method analysis of truss. Okay, analysis of truss. So please try to understand this. This is very, very important. Please try to understand this, because this is there will be two question for stiffness method in final exam, and quiz. 5% quiz also will come from stiffness method. Okay. So please look at your lesson plan. So you will have 40%, 10 for assignment, and 30% from test. Final exam is 60%. So for final exam, 2 questions will come from stiffness method, and thrust is a compulsory question for final exam. Another one is between beam and frame. Okay, so you have no choice. You need to try to understand. Please watch all my video regarding this topic. So actually I have discussed few times, more than 2-3 times, maybe more than that, discuss about the same question. Okay, the same question, and also I also discuss quite a lot of past exam paper about thrust analysis using stiffness matrix method. Okay, so I think that's all for this session, and you have to submit one thrust question as usual once a week. Okay, so for this week you have to submit trust question. Please find one trust question. Find in any maybe in past year exam paper, maybe using Google. You just need to Google or you can also draw on your own and then try to solve the unknown displacement, the unknown reaction, as well as member forces in the trust. Okay, so that's all for this session. Thank you very much. Inshallah tomorrow, tomorrow we will discuss on the effect, 3 effect, temperature changes, fabrication error, and support settlement. So all will be referring to the textbook, example in the textbook. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, Doctor.
Waalaikumsalam. Thank you, madam.
Thank you, Doktor.
Okay.
Thank you, madam.
Thank you, doctor.